And you can hear me? I hope so. Cool. Okay. And there's a clicker thing, right? Uh, or no? I can just click here or here. Yeah. Okay, cool. My name is Karl Munthe. I'm going to tell you kind of qualitatively how we model the heart, both mathematically and numerically. And yeah. Thank you to my supervisors, Henrik, Samuel, and Joachim. Yeah. Okay, just really quickly, I should mention that normally, or not always at least, you don't model the entire heart. You just choose a chamber. There are four different chambers you can choose. And the one I normally work with or only work with is the left ventricle because that's the one that spews blood from the heart out into the body. So then what we want to answer now is what triggers growth, essentially, and also what characterizes healthy and unhealthy growth. So you can, for example, work out, and then you're going to have a little bit bigger heart. You're going to have a thicker heart wall and a bigger cavity. So you're going to have a thicker heart wall, probably because you're going to be pumping more blood per pump. And you're going to have a bigger volume because you're going to need more blood in the heart for every pump as well. But also, you cannot work out and just have high blood pressure. And then you're also going to have a thicker wall, but maybe you won't get the increase in the cavity size. Or you can have just heart failure, which is also very bad. And then you're just going to have, for example, in this case, just a thinner wall. But now, if we try to look more into the cellular level, what is actually happening when the heart is growing, and you don't actually grow by increasing the amount of cells or decreasing, you're just growing by changing the cell shape and size. So you're actually born with the number of heart cells you're going to have for the rest of your life. And if we just have a very simple model, this is the left ventricle again, and just think of this is how it is in the like baseline state. Then I like to think of the cells just as kind of like a bag of springs. And then the reason I like to visualize it this way is because if you take a spring, stretch it out, and release it, it's just going to be oscillating back and forth. And that's kind of like what the heart does when it's pumping all day. But then you can have, for example, concentric growth, which is a thickening of the heart wall. And that is kind of like adding springs in the cell in parallel. Or you can have the opposite, which is eccentric growth. And then that is a thinning of the heart wall. And that's kind of like adding springs in the cell in series. And if you remember from your mechanics class, if you add springs in parallel, you have more resistance to the stretching now. And if you add them in series, you're going to have less resistance. So it's less stiff. And that's also what we see in patients. If you do have a thicker heart, it's also going to be stiffer. And if it's thinner, it's going to be softer. Okay, but now the fundamental question is how does the heart know when to grow and how to grow? Does it want to add springs in series? Does it want to add them in parallel? Um, and also, what triggers growth? So, for example, growth might be triggered by stress. So you can imagine blood coming into the heart at a higher rate. So now there's a higher amount of wall stress on the inside of the heart, and that might trigger the growth. Or, for example, you can have growth that's triggered by strain. So maybe now the blood's coming in at a higher rate and there's more pressure, but the reason it's growing is because the heart isn't able to contract as much as it actually wants. So maybe the heart is actually optimizing for some contractility thing or optimal contractility, I guess you would call it. And then before we go on, I just want to do like a quick mechanics refresher so we're all on the same page. Imagine you walk into, I don't know, a hospital or something, and then you look at someone's heart and you draw a grid on it. And then you leave, come back a few months later, and then you see that it has deformed. So we call this initial state the reference configuration or initial configuration or something like that. And we say it's mapped to a deformed configuration by the motion that is sometimes denoted with a phi, takes in a vector and then outputs a vector. Okay, but we know that a bunch of these interesting phenomena happen because of shear stress, for example. And then you can't just be looking at how do points move independently. You have to look at how points move relative to each other. So then you have to look at, for example, a basis or just vectors that you make in the domain. And they can only be mapped if you take the derivative of the motion, and then you map them to the deformed configuration. And this is normally denoted F with an F. This isn't the force, it is just a deformation tensor. Okay, now we can do a concrete example. So a very simple example in FEniCS, and then you have first some undeformed configuration. Imagine this is just like a little chunk of the heart, and then you stretch it, and then because we're on computers, we can decide when it's supposed to grow. But so no growing is happening; it's just stretching. But then you said this stretch triggered some growth, and in this particular case, maybe the growth wanted to optimize for, or like wanted to keep the original rectangular shape of the initial condition. Okay, we say the first deformation is the elastic deformation, so we denote it with the subscript E. And then we say the second deformation is the growth deformation, and it has a subscript G. And then we normally, all the stress that occurs, you normally just contribute that to the elastic deformation. And then the total deformation is simply just the product of these two tensors. Yeah, but this is obviously a very simple example. Normally, real life is a lot more complicated. So the flow of my program is something like this. You have an initial FG that is just the identity tensor. Nothing is happening. And then you have some stretching or something that occurs. And then remember, the total deformation is just the product of FE and FG. And then you solve for FE, because that's the only thing that stresses the heart, essentially, or whatever your material is. And then you have the divergence of stress equals 0. That's what you're solving for. When you solve that, then you get to trigger the growth, essentially. And then you update FG. But since we said FE is dependent on FG, we have to go back, and then we have to update FE again. And then we keep on doing this cycle until FG approximates, or approaches the identity tensor. And a very, very simplified version of the code that you can think of that solves this is that you use the just solver.solve in FEniCS-X that you all probably have written. And that is obviously solving the divergence of stress equals 0. And then the update, you have some stress field, the strain field, and then you use that to update FG. And then I just have the module where I try to put all the growth models I can think of. And yeah. Okay, so the fundamental problem, to reiterate that, is that you have some elastic deformation that is triggering some growth deformation, but that growth deformation is now triggering the elastic deformation again. So it's hard to decouple these. And we also know that deforming different materials is different, essentially. And that's determined by the material model, obviously. And we are working with hyperelastic models, so we're only Neo-Hookean and Fung and the basic ones, kind of. And in the exact same sense, you have growth laws, and they are also determining how the growth deformation occurs. And what I want my program to be doing in the end is essentially just taking a bunch of the growth laws I don't know if you've read about them, but someone has read about them, and a bunch of the material models and see how they combine to simulate growth. So for example, you want to choose this growth law and this material model, then you can do a simulation, see how that turns out, and then, or if you want to do, for example, this growth law and this material model, then you can compare those. Or if you want to create your own growth law, you can just see how it compares to all the other ones, and then you can see where are they good or bad, etc. And some preliminary results are, these. So these are 4 different combinations of growth laws and material models. And the first, 1 and 2, we see they don't go back to the rectangular shape of the initial condition. Oh, I should mention, this is the exact same experiment or simulation as the one I mentioned before. You stretch and then you let it grow. So 1 and 2, they don't go back to the rectangular shape. 3 and 4, they have a little bulge. And that's kind of nice that you get different characteristics, because then you can go to the clinicians or whoever looks at hearts growing and ask them, what do you see? And then you can slowly iterate and get, in the end, a better understanding of the mathematics that describe growth. And that is basically all I had. Thank you for your attention.